Hello Math 1100 students. Let's begin chapter 4, linear and quadratic functions. We are going to cover linear functions now in week 6, and then we are going to spend entire week 7 for quadratic functions. Okay, here we go. Linear functions and linear models. This kind of function is called a linear function. Y equals mx plus b. That's a line. The slope-intercept equation of the line. And that's why these kind of things are called linear functions. Graphs of linear functions, here's a standard form, the slope-intercept form. And this program is randomized, so you can run it again and again and again for different y-coordinate and slopes. You can play with that. What is m, the slope? What is b, y-intercept? You should remember those. Now here is the slope point form. This time, slope is m, and it is running through x0, y0. Play with this because this program is also randomized. Now, 2-point form. This is going to be useful when we have a data set and we have 2 points. Join those together and get a line. And that equation, that y equals f of x form, is the linear function you're looking for. And this expression will be useful for the coming example here, example 1.4. So please remember. Okay, that was a quick review of graph of linear functions, which we went through already in chapter 2. Now, let's go back to chapter 2 again. What is the most important concept of a graph of a line? That was the slope. Rise over run, or the difference of y-coordinate over the difference of x-coordinate. Here in chapter 4, let us add one more term, the average rate of change. So average rate of change is also called the slope, and it is the difference of y-coordinate over the difference of x-coordinate, delta y over delta x, or in graph, rise over run. And for any line, the average rate of change, the slope, always stays the same. So that's the key point for any linear modeling. Do we have the same average rate of change all the time? Okay, here are a couple of examples. Please stop the playback and read through the problems. The first problem is about population model. It's about the growth of E. coli bacteria. And here's a data set. From starting time to 5 hours later, and x-coordinate is a time, 0 to 5 hours, and y is a population measured in grams. Okay, let's plot all these dots. Does it look like linear? Maybe a bit hard to tell. To me, it doesn't look like linear. Maybe that's because I already know the answer. How about you? Okay, that looks a little bit better. Clearly, this is not a linear model. You see, this is supposed to be the line of best fit. So the line that minimizes the error, the vertical error, and you can see points are not running through any line there. And this is supposed to be the best line. Why is this not a linear model? And that can be answered algebraically. You can calculate the rate of change or the average rate of change at each interval from interval 0 to 1. The first computation, the difference of y-coordinate over the difference of x-coordinate in that interval. And in interval 1 to 2, interval 2 to 3 hours, interval 3 to 4 hours, and interval 4 to 5 hours. And then, of course, theoretically, bacteria will grow even more, so you can consider even more if there are more data. In any case, if you calculate these, do we have the same average rate of change? Clearly no. Therefore, this is not a linear model. As a matter of fact, you can join each pair of points and get different line segments. And if I do that, clearly you can see that this kind of polygonal path is not a linear path. As a matter of fact, it'll turn out that this is an exponential model. We're going to study this kind of modeling in, let's see, some place in chapter 6, I think, in the latter half of the course. Clearly, this is not a line, it's a curve. So why did it fail? The average rate of change did not stay the same. Now, how about the second example here? This time, the average rate of change will stay the same. Now, here's a data set. And then we have age in x-coordinate, 20 to 70. And then the heartbeat, 50 to 37.5. And then each 10-year difference in age, look at the dropping of y. We have 2.5 of drop. And we end up with this kind of dot, and well, do they look linear? Certainly looks like it. And along with the line of best fit, yeah, now this time it's really clear. They're all coming from the same line. So this is clearly a linear model. And of course, let's check those with computation. Let's calculate the average rate of change for each interval. Interval 20 to 30, here's go. And then interval 30 to 40, here we go. And then interval 40 to 50, here it goes, and so on and so forth. They all have the same average rate of change. That's the quintessential nature of the linear models. Same average rate of change all the way. Same slope all the way. Okay, we went through linear functions and the concept of average rate of change versus slopes. And also we touched linear models too. Let's continue working on linear models. Here's a summary version of what we said. If the average rate of change stayed the same all the time, then we can use linear models, and vice versa. Whenever you have a linear model, you can expect the average rate of change, the slope, always stay the same. And then here's the example we just went through, so I'm not going to repeat it. The first example, we have different average rates of change. So this is not a linear model. As you can see, we have a curved model. It's an exponential model, to tell the truth. And in this case, we have the same average rate of change all the time. And not coincidentally, we have a linear model. But then again, that was a simple case. We have just one function and consequently just one type of average rate of change to consider. Some cases, we may have to deal with more than one linear models put together. And here's an example problem. We have two linear models. The first one here, S, is given by this equation here with the average rate of change of 15. And then the second model, D of P, has the average rate of change of negative 3.75. And we have to answer some questions about these two put together. Now, please stop the playback and read through the problem. This example is coming from economics. Partly in business too, but mostly in economics actually. So supply of a certain good is S of P, and the higher the price, the more supply. That's because the price goes up, then the manufacturer will try to make more so that they can make more money, basically. Demand, on the other hand, works backward. If price goes up, and consumers will try to cut down spending, so the demand goes down. Of course, that's for normal goods. There's some abnormal luxury goods with some swagger factor, such that price goes up and then people want to buy even more. But those are kind of exceptional, and then those kind of bubbles eventually pops and die out. So let's consider the normal case. So supply will go up as price goes up. Demand goes down as the price goes down. And then here are some questions that you have to answer. Find the equilibrium price, where supply and demand become the same so that price will not change. And let me mention one more thing. If supply is bigger than demand, then you're going to get surplus, so price will come down. Vice versa, if supply is less than demand, then the price will go up. So equilibrium price, when S of P and D of P are the same, that's when we have little change of price, the equilibrium price, and that's what you're looking for in this problem. Okay, we have A, B, C, and let's answer these questions, but let me change the order. Most of the time, it's going to be better to use technology to graph first and then solve the problem rather than the other way around. So I'll do C first. Supply is blue and the demand is red. So as price goes up from 0 to 400 here, and supply goes up and then demand goes down. And then if the price is too low, then obviously manufacturer will not make anything, because if it is too low, then they're going to lose money by just simply making. So it's natural that this thing begins positive anyway. And this graph will not extend forever. At some point, demand will go down to 0, and that's going to stop. And everything here is actually an approximation, to tell the truth. They cannot possibly stay in straight line. For a small period of small interval, we can approximate the demand and supply with linear models, but in long interval, they must be curved. Anyway, let's suppose this model, and then let's find out the equilibrium point here. What is the p-value here? What's the price here? Well, S of P, D of P, set these equal and find P, and that was easy. I'm using the wiggly equality sign here to be a little bit precise, because everything is modeling, so nothing is precise, nothing is accurate. If you use equality, I don't mind. Anyway, solving this linear equation is the easy thing to do, and then you can verify that through a graph like this. At $200, indeed, we have equilibrium. And then at this equilibrium, the amount sold, amount bought, that's going to be 2,100 units. Okay, and then determine the price for which the quantity of supply is greater than quantity of demand. That is, more supply than demand. Supply is blue and demand is red. So graphically, blue should be bigger than red, right? More supply than demand, so I'm looking at this right-hand side. So if you look at the graph, it's a bit easier to deal with. So I'm looking at this part, and this is algebraic way to solve it. More supply than demand, so strict inequality this way, you can solve it algebraically like this, but the picture will help you. I'm looking for this kind of price range, greater than $200, so that blue comes above red. Okay, that was an example of a linear model, or actually in this case 2 linear models put together, where the models themselves were explicitly given. We're going to study how to get these models to begin with, these equations to begin with, a bit later, and probably in the latter half of the next video down here, so please be tuned. At this moment, we'll stop here and see you soon.